Okay. At number 0, we are going to use the BLAKE3 hash algorithm and specifically the BAO encoding format for syncing content address data. And I want to explain a little bit how this is going to work today. So BLAKE3, what is BLAKE3? BLAKE3 is a cryptographic hash function. It's an evolution of the BLAKE2 family of hash functions. And there you can see the difference, whereas BLAKE2 was a family of hash functions, BLAKE3 is just one hash function, which is meant to be usable for all kinds of use cases. So the tagline on the repo is one function fast everywhere. And it supports all the typical use cases of hash functions. It supports massive parallelism, both SIN, single instruction multiple data, and multi-threading. Fast, as you can see, the project prides itself in being faster than other cryptographic hash functions, and it makes this possible by 2 ways. One is single instruction multiple data, so basically it processes data in chunks of 1 kilobyte, and when processing these chunks of 1 kilobyte, it is using all instruction pipelines of your CPU. And the second thing that it uses to get very fast is that it's using fewer cryptographic rounds than other hash functions. If you want to know more about this aspect, there's a paper called Too Much Crypto, where that is explained in more detail. But that's not the topic of today. So how does it work? Basically, there's 2 functions that make up the hash function. There's one function that can take a chunk. A chunk is a blob of up to 1024 bytes. And it takes this chunk. It takes a chunk number, which is kind of the offset of the chunk and the file. And it takes a Boolean flag, and then it produces a hash. A hash in case of BLAKE3 is a 32-byte blob. And during this computation, there's massive use of single instruction multiple data instructions. This is implemented for all kinds of architectures, so both ARM and x86, x64. And now, what do you do if you have a file that is larger than a single chunk? There's a function that combines multiple hashes to a new hash. This is called parent CV. CV stands for continuation value, but basically just a function where you put in 2 hashes and you get back a hash. And in addition to the 2 hashes, there's an additional parameter called isRoot, because the root needs to have some special treatment. So basically how this works, if you have these 2 functions, is that you can build a binary tree of chunk hashes and basically condense or compress your chunk hashes all the way to a single root, which then is your final hash. The tree that you'll get tends to be lopsided, so it's always filled on the left side and may not be filled on the right side. And as I mentioned, the root gets special flag to make sure that basically to prevent length extension attacks. During the computation of this tree, in addition to the single instruction multiple data that is used for computing the individual chunks, you can also do multi-threading. So you can basically say the left-hand side of the tree gets done by one core and the right-hand side of the tree gets done by another core. Once you have a large file and you want to compute the hash of multiple chunks, the operation is big enough that it's valuable to have multiple cores working on it. For a single chunk, it would not be worth it to split it up on multiple threads. So in BLAKE3, this binary tree is entirely ephemeral. So you basically use this logical binary tree to compute the root hash, but the binary tree is not stored in any way. So that all sounds very complicated. So now let's take a look how this looks in detail. So if I have a single chunk, which is 1024 bytes or less, then everything is very simple. I take the chunk, I put it into the chunk hash function, I set the root flag, and I get back my root hash. The root hash here is dark gray. Now let's see how what I do if I have a bigger tree. If I have two chunks, I cannot put the two chunks into the chunk hash function at the same time because they are too big. So I call the chunk hash function twice, once for the first 1024 bytes and then for the rest. And then I get two chunk hashes. And now, obviously, I don't want two hashes, I want one hash. So what I need to do is I need to introduce an intermediate node, this one, which is composed of the left and the right chunk hash, and then take this node and put it into the parent CV function to compute the final root hash. This is just an intermediate value that is stored somewhere in the builder when you build a hash. It is not persistent anywhere. So now let's see how it evolves when you have a bigger tree. Now we have three chunks, and you can see what I mean by the tree being lopsided. So we have three chunks. You compute the chunk hash for all three chunks. And now what do? The first two chunks make up a complete tree. We got this parent node. And now we have this one chunk which is left over. So what we do is we create another parent which takes as a left child the completed tree, and as a right child this individual chunk that we have left over, kind of. And then again we compute the parent CV here and get back the root hash. So now we got a full tree again, so it's no longer lopsided. And here we can see it gets lopsided again. Always the left-hand side of a tree is always full, and the right-hand side is either full or it might be incomplete. But there's no problem. It's still very clearly defined how a tree is constructed. So this is how it continues. Now we get on the right-hand side, we get a little tree with two hashes, and that basically goes into this node, and this goes into the root hash. And so now we're done. Now we got 8 chunks. As you can see, the last chunk is it can be full, 1024 bytes, or it can be less than full, but it needs to contain at least 1 byte. And now we got a symmetrical, completely full tree and compute our parent hash. Okay, so that's BLAKE3. And here you can see why this is great for parallelism. Imagine you had a file like this, and you're computing the root hash. You could say at this point, I will let one core compute the entire left side of the tree, and another core compute the entire right side of the tree. So both cores get a meaningful chunk of work to do, and then at the very end, you need to combine the two and compute the root hash. So it parallelizes like a dream. It will use all cores. Now, BAO is basically the same as BLAKE3, except that this tree that I've been talking about is no longer ephemeral, but it is persistent somewhere. So what is that good for? Why do the effort of persisting this tree? It allows something called verified streaming of either the entire data or a range of data in this tree. Now, what is meant by verified streaming? There's 2 modes to persist these outboard to persist the tree, either in an outboard way where the hashes are in a separate file, or in an inline way where the data and the hashes are mixed. Now, what is meant by verified streaming? One thing is I can verify, let's say I want to send some data to a remote client, and the receiver can then verify the data while it is receiving the data. So unlike other hashes where you basically do a big download, 1 gigabyte, and then you compute a hash at the end and notice that you've downloaded the wrong thing, In this case, you will verify while downloading, so you will immediately notice when you get wrong data. Now let's take a look how the data encoding works. As you can imagine, as you write the tree, you will always first write the data chunks, and then whenever you have a new data chunk, you will be able to compute the hash. Whenever you have two new data chunks, you'll be able to compute a parent hash, and so on. So it's very natural in the way that hashing works that you'll be able to compute the parent nodes only once you got the child nodes. So, and this means you will get the data in post-traversal order. And now, in what order do you need the data when you want to send it over the wire? You need it in exactly the different order. You need first the two hashes immediately below the root to connect kind of the root to the data. And that is why as the encoding is done, at the very end, it flips from post-traversal order to pre-traversal order. Okay, now there's two different encodings. One is inline, where the data is mixed with the hashes. One is outboard. Let's take a look first at how inline works. So there's an 8-byte header, which is the total size of the file that is being hashed in little endian. Then there is two different things that can come: 64-byte tree nodes, which consist of two hashes, or data chunks, which can be which are always 1 kilobyte, except for the very last chunk, which can be less. And these also come in pairs. Okay, this is easier to understand if you have a drawing. So here we got the same tree from before, except now we want to compute a bow encoding. So here we got a single chunk. That is very easy. You just compute the hash of the chunk, and that's your root. And by the way, this is not being persisted. The hash here is not being persisted because it's a root hash, and the root hash you just give to the root hash is already the end result. And as you can see, post-order traversal is just the data, and pre-order traversal and bow encoding means just having the data and prepending the size. Now this is very boring, so let's go to a bigger tree. Now we got two nodes. We compute the two chunk hashes, C1 and C0 and C1. And compute the parent hash. And now in the post-order traversal, we write first the first chunk, then the second chunk, and then these two hashes. So these two together are 64 bytes. And then this is being flipped into the pre-order traversal order. So we have the size prefix, then we got the two hashes, and then we got the two nodes 0 and 1, the actual data of the nodes. Of the chunks. Now, why? Maybe this wasn't clear. Why does it need to be in pre-order traversal? Imagine you have P0. You got the parent hash. You got the hash of the entire thing. What do you need to validate that this hash actually corresponds to the data that you're being sent? You need this immediately, the thing that is below the parent node. So this C0, C1, the two hashes, needs to come first in the encoding. And that's exactly what we get here. We got first the two hashes and then the two chunks. Now, as the tree grows, now we got lopsided three chunks, and we got these two parent nodes. As you can see, in the post-order traversal, we first got the two chunks, then the two chunk hashes, then this intermediate, and then this last chunk, and then this parent node. So this is the one immediately below the root. This is this. And then as it gets flipped to pre-order traversal, you got the size prefix, and then you got the thing immediately below the root as the very first thing. And then we get here basically this these two hashes, the two chunks, and the third chunk. You already know the hash of the third chunk because it is the second element in the first tree node. Okay, as this gets bigger, you can see that the encoding gets a bit more complex, but fundamentally it's still the same. So now we got a Bauer tree of 8 chunks. And in the pre-order traversal, again, we got the node immediately below the root comes first. Then the left child of this. Then the left child of this node. And then come the first 2 chunks. Then the second 2 chunks, prepended by the 2 hashes of them, and so on. So the pre-order traversal, the Bauer encoding contains exactly the hashes and the data in the order in which we need it to validate that the data is correct. Okay, so I mentioned that there are 2 different encodings. There's the outboard encoding and there's the inline encoding. Now let's take a look at what the outboard encoding is good for. It is, again, there's a size header, and then the outboard encoding only contains pairs of hashes. So basically, you can get the outboard encoding by just removing all the data from the inline encoding. And what's great about this is that we basically have 2 files. You got the outboard and the file itself, and we can keep the original file unchanged and still read from it. So imagine you have a big file, let's say a 4 GB movie file, and you want to share it over the network. One way to do it would be to ingest this file into some kind of system that can share data over the network. But that means that you have the data no longer on your disk, but in your system. And then you might not want that because you might want to access the data on your disk, even though you share it. And that is why it's very useful to have the outboard, so you can share a file while leaving it in your file system. Okay, so here we see how the outboard works. Basically, we got our tree, and we got the Bauer encoding, which contains the hashes and the chunks. And the outboard is nothing more than just the hashes of this tree in depth first, left to right, post-order traversal order, pre-order traversal order. So basically first this, and this, and this, then this, and so on. Slice encoding. So one thing that Bauer can do is it can stream an entire file in a verified way. But what if you only want part of the data? Let's say you have a video and you want to seek at a certain position in the video, but you still want to be able that the video is actually the one that you've requested with your hash. So one example how this would work is HTML range requests. So what this slice encoding gives you is it gives you the data at the position you've requested, and it gives you a guarantee that this is actually the correct data of this hash at this position. So it verifies not just that the data is somehow related to the root, but it also verifies that the data is actually at the correct position. Now let's take a look how slice encoding works for a small slice here, marked in blue. So to basically validate that this piece of data is related to this root hash, we need to somehow connect the data to the root. And to do that, we need a path from the root to the data. So we need the branch node immediately below the root, and then this one, and then this one. And now we got the hash for the data of chunk of set 1. Do we need this chunk? No, we don't, because the range does not intersect this chunk. Do we need any of those chunks? No, we don't. So basically, the encoded slice contains a path from the root to the chunks we are interested in, and only the chunks we are interested in. But as you can see, there is a little bit of overhead. Even though we've requested only a part of this chunk, the encoding will contain the entire chunk. But the overhead is not that big because these chunks are 1024 bytes. So the maximum overhead that you can get is two chunks, basically, 1024 bytes times 2. And if you imagine seeking in a movie, then this is really no big deal. Okay, now we got a different slice encoding for a part of chunk 3 and 4. And as you can see, the path to the first chunk now looks different. Now we need the node immediately below the root, the next left child of this one, and then the right child of that one. And then again, we only need these 2 chunks, number 3 and number 4. All the other chunks are being omitted. Okay, so that's what the slice encoding, how the slice encoding works. And now let's get to something that we've implemented at number 0 to make the bow outboard more efficient. It goes back to an idea of the original author of bow, but we have implemented it because we need it, basically. So imagine the outboard consists of one hash, one direct parent hash per chunk. So it's 16 bytes per chunk of overhead. And then, since it's a binary tree, the number of nodes is 2n minus 1. So on average, the overhead for each chunk is 64 bytes. 64 bytes for each 1024 byte chunk, meaning the overhead is about 1/16. And that is actually quite a lot. Imagine you have a 1 terabyte file, then the outboard would be 64 gigabyte. And 64 gigabyte is too big to keep it in memory, basically. Now, let's say you want to somehow still have outboards, but you don't want to have them so big. One thing you can do is you can just basically take this tree, and the tree still exists. This tree is fundamental to the way how BLAKE3 works, but you just don't persist the leaf nodes of this tree. So the nodes at the lowest level, you don't persist them, but you just compute them whenever you need them. And that means that your normal bow encoding gets a little bit smaller, as you can see, and the outboard also gets much smaller. And that means you can have, for example, you can have larger files for which you can keep the outboard in memory. This is a chunk group of 2, so basically our kind of chunk group size is now 2 BLAKE3 chunks, or 2048 bytes. And you can increase this, obviously. Now we got a chunk group of 4. And now, as you can see, the outboard is basically tiny. And if you had a chunk group of 8, for this particular file, the outboard would vanish completely. But imagine you have an outboard chunk group of 8. That means the overhead of storing the outboard is divided by 8. And that's quite a big advantage because now you can have the outboard in memory for giant files. And also basically just have less overhead persisting the outboard. And the downside, of course, is that you have to recompute these hashes whenever you need one of the hashes below the level at which you persist. You need to recompute it from the data. But since BLAKE3 is so fast, this is not a big overhead. It's totally acceptable. You won't even notice, basically. And now let's take a look at something called size proofs. Imagine you have a hash, and you want to know how big the file is that is behind the hash. Now, if you have a peer that claims to have the data, you can obviously ask the peer to tell you how big the data is. But let's say you are in an untrusted scenario and you want to be really sure that this is the size, that the peer doesn't lie to you. So what you can do is the following. So here we got a bow tree with 8 chunks. And what is the minimum that I need to send to prove that this thing has a size of 8 chunks? So what I need to send is obviously I need to connect. So the only thing that has information about where it is in the file are the chunks. So the last chunk knows that it is at offset 7 because it has been computed with the chunk offset. The hash of the last chunk has been computed with the chunk offset. So I need to do the typical thing. I need to somehow connect the data to the root. So I need to persist the path from the root to the data. So I need to persist this node immediately below the root, then the right-hand side of that, the right-hand child of that, and then again the right-hand child of that. Basically, I go to the right until I get to a chunk. And then you might think that this would be sufficient to at least say that you have 7 chunks, but it turns out that it is not, because you don't know what exactly happens on the left-hand side here. It could be that on the left-hand side you have a giant tree. So what you need to do is you need to include the chunk in the size proof. So the last chunk, number 7, needs to be included. And then how the proof works is that you have your last chunk, and you know that it should be offset 7. So you compute the hash of the last chunk with the chunk offset 7, and then you get C7, the hash of chunk number 7. And if this was in a different part of the file, then this chunk would not match. Basically, this is the size proof. And as you can see, it has a certain overhead. It is 1 chunk at least, and the path to the chunk. But it turns out that this is the overall overhead is not that big. So a size proof would be something like 1 kilobyte for small files and 2 or maybe 3 kilobytes for giant files. So size proofs, if you have chunk groups, you might think that now you cannot do size proofs anymore, or that you have to add an entire chunk group to your size proof, but this is not the case. Imagine you have a chunk group level of 4, so 4 chunks get combined into 1 chunk group. But that doesn't actually change anything. You can still compute a path from your root to the rightmost chunk. The only difference is that these intermediate nodes here, so the one immediately below the root, you can just take from the outboard, but the one to the right, you have to recompute from the data. And the one here, you also have to recompute from the data. But it doesn't change a thing. So basically, a size proof, even if you have chunk groups, is just a single chunk and a path to the root. And that means basically that chunk groups are kind of an implementation detail of the storage engine. Okay, so this is the end, except maybe that I got a little thing that I've been thinking about. So one thing you might notice is that there is this annoying post-order traversal, which then flips to pre-order. And what if we keep the output in post-order? What it changes then is that the output is mostly append only, and you only have changes at the very end of the output when appending data. And then you might even think about keeping the nodes that are actually changing in a separate file. So what I mean about output is mostly append only, let's take a look at the bow encoding. Here. Now take a look at the bow at the very bottom here. And as you can see, as data gets added, the data chunks move around in the file. And that is not good, because basically every time you add a little bit of data to your file, in a case, for example, where you have an append-only file, you would have to basically completely recompute the outboard, or even the bow. And if you keep things in pre-order, in post order, then you don't need to do this. Now let's take a look how it looks if I keep things in post order. So I got a tree here. The left side of this tree is never going to change again. So 0 and 1, assuming I only append data, 0 and 1, chunk 0 and 1 are never going to change. So this parent node of the 2 is also never going to change again. This node is kind of unfilled, so it might change again. But as we see, the nodes that might change in the future, if I append data, are at the very end now. And now I got a full tree, meaning that nothing can change. Now I got a incomplete tree again. Yeah. And now if I scroll through this quickly, you can see that the post order outboard is only being appended to except for a very, very small part of the data at the very end. And that's it, basically. That's how BAO works.